In this example, we'll look at a different data set to use with our regression. So here we have 10 data points. We measured 10 homes of different square footages, and we want to see how much electricity they use per month in kilowatt hours per month. So using this data set, we'll be able to, if we have a house between 1,290 square feet and 2,930 square feet, make an estimation as to what their monthly electric usage should be. So the first thing we want to look at here is put in our independent variable, which is the size of the home. So again, we have 12 entries here, so we can put that into MATLAB. And how much electricity they use per month. So I'll just call that KW here. Okay, put it all in 1954. All right, so we have all of our data. Let me make sure we're always starting with our clean slate. All right, so we have all of our data entered into MATLAB. So I don't know in this example necessarily what the relationship should be between how big the home is and how much electricity they use per month. So in this case, we're going to start with just plotting the data so we can get a general idea of what we are dealing with here. And it's raw data, or it's empirical data, so I don't want it connected. I want it as discrete points. And I'll label it. So this is our home size, square feet. And our y-axis is how much electricity we use. And that was in kilowatt hours per month. So this is our data that we collected from the homes, and we can see the pattern we have with our home size versus the electric usage on a monthly basis. So based on the previous example, we can start with just a simple approach to fit a function to our data. So let's just start with a fit type of a linear relationship like we saw did work pretty well in our last example. Right, so we can use either poly1, or I'm going to type it explicitly here as the a0 plus a1 times x. So that's our linear fit. We have our intercept a0, and we have our slope a1. And to run our fit, like we saw in the last example, I can use the fit command. I have my independent variable s. I have my dependent variable, the monthly kilowatt hours. And then I'm going to start by trying a linear fit on this data. And we see that it doesn't like this yet because, again, s and kw both have to be column vectors for this fit function to work. So I'll rerun this and not misspell fit type. Okay, so it gives us, if we use this linear fit here, let's actually plot this and we can see how it actually did perform. I want to have a range of home sizes that I'm going to look at, so I'll make a linspace between the minimum value I had of s and the maximum value I had of s, and I'll put 1,000 points in between. So on the plot, I'll put my estimate on top of this, like we saw in the last example. So I want to plot S2 versus f of S2. So this will be from my regression. And again, I'll make this a red dashed line. And so we know what's going on. I'll put a legend. And so it looks good. I will put it in the southeast corner. Okay, so here's our original data as the points, and our red dashed line is using a linear regression in this case. All right, so we look at this, and the the red line doesn't agree, compared to the last example where the red line agreed pretty well with our data. Here the data is pretty far from the red dashed line here. So visually it doesn't look like it's necessarily a great fit to our data using that linear relationship. And if I go back, I can also use this goodness of fit to judge how well it goes with the data as well. Right, so we see here, we'll judge just in this example by the r² value is 83%, which is actually not too bad for most data. It does a decent job of predicting it, but there might be a better function to use than a linear fit for this particular data set, and that's what we want to explore. We can always come back to the linear fit and use it if we want to. But we see especially at the end point here that last, for the biggest house, it's not really well fit by this line. And then down here for the smaller houses, also not a very good fit. So let's try a different fit. Now again, in this case, I don't really know what the function should be that fits it, so I'm going to try, I'll stick with a polynomial for now and just see how it performs. So I'm going to use a second order polynomial, which means I have a constant term, I have an x term, and then I have an x² term in what I'm doing. So let me rerun this now with this fit type, and this would also be poly 2 we could use. I'll show that in a second. We get the same results. So if I rerun this with a different fit, and now we see when I put on my regression line, this red dashed line, that it appears, at least visually, to fit my data much better than the linear fit did. So the points are much closer to the line, so it does a better job describing this relationship. Right? And if I go and look at the goodness of fit for this curve, I see that my r² value is 98%, so it's higher than it was when I was trying to use a linear fit on it. That doesn't necessarily tell the whole story if it's a good fit or not, but we see, again, the r² value tells us kind of how close are the original data points to the regression line. Usually if we get a 98% r² value, we should probably be satisfied. But let's just see, for example, what if we try to use an even higher order fit? Let me add a cubed term to this and see how it performs. And if I rerun this with the higher order fit, we see actually it looks pretty similar to what we saw in the second order fit. And if I look at my r² value, it's only a little bit higher than it was for the second order fit. They're both around 98%. So in this case, we would think which is a better fit to use. This does technically have a better r² value, which means it adheres to the original data just a little bit better. However, kind of a general philosophy of fitting is that we want to use the simplest fit possible to describe our data, unless we know the underlying function that's creating that data, which we'll look at a later example. So in this case, our third order model for the fit didn't really do that much better a job than the second order model. The second order model did do an appreciably better job than the first order model. So if we were only looking at polynomial models here, I would say that the second order model would be a good one to use to fit the data that we collected. Because it's a simpler model, it used fewer terms. Here, again, what are we trying to find when we use the fit? In this case, we're trying to find these four coefficients, this A0, 1, 2, and 3. So there are four things we're trying to do. If we go to our second order model, we've now reduced it into only 3 variables that we're trying to solve for when we're going through the regression. So going back to that second order model, again, A0, 1, and 2, so only 3 things we're trying to solve for. And just for the sake of example, I can use, because this is kind of a standard fit using a second order polynomial, if I use this poly 2, it's actually going to do exactly the same thing as if I explicitly wrote it out. The only difference is here when I look at f, they use different names for the coefficients. They're using P1, P2, and P3. If we look at how this model is constructed, I have the P1 times x squared, P2 times x, P3. If I go to the way I was doing it, and we look at how f is defined, it's just a little bit different. So here I have a0 plus a1x plus a2x squared. Now let's look at the utility, again, of using this regression. So I have this nice regression line, this red dashed line here, and we can use this to make predictions or estimates for buildings that we did not actually measure. So in this case, we only took 10 home sizes in our sample. So let's say that someone wanted to build a home that was 2,100 square feet, and we were interested in estimating how much do we think they're going to use in electricity each month. Again, 2,100 square feet was not one of the 10 houses that we did measure, but what we can do is, now that we have this fit, this F, I can put in, if I have 2,100 square feet, what can I estimate my monthly electricity use to be? If I type that in, it looks like I'm going to use estimated 1,837 kilowatt hours every month. And if I reference back to the plot here, I can do this graphically as well, since that's where these are being produced. If my X value here is 2,100, if I drag it all the way along, I get 2101, pretty close, that same estimate, according to my regression line, about 1,837 kilowatt hours.